Hello, I'm Joel Fischer. I'm the lab manager here at AMETEK. The following presentation is one that I gave earlier this year at the Global Pouch Forum. This was a leading innovation in flexible packaging conference. The topic of the forum was really about sustainability in packaging. That's really key in industry today and really across the globe. For example, in Europe, uh, consumers, they're demanding sustainable package, and the demand has risen to 81%. In the United States, 80% of adults that are under 34 willingly pay a premium for sustainable products. That's really interesting because if you look at packaging on the shelf, and maybe you have two shampoo bottles, one next to each other, one might be a little bit discolored because it looks like it's from recycled polymers or recycled plastics. Would have just been a few years ago that would have been like a negative connotation, whereas today that's a very positive thing. That's a very forward-thinking company that's going to be putting their products into recycled materials, and there's a really goal to make those recycled materials look recycled because it is attracting brand owners. In Asia as well, 60% of customers believe the brands themselves must really adopt sustainable packaging. So the clients are looking for it, customers are looking for it, and it's an innate expectation from the brand owners to provide sustainable packaging. When we look at the trends in sustainable package, a really good litmus test for it, or a really good example, is what Bob's is doing. And I was able to borrow one of their slides from an earlier presentation this year that they presented. And it's really unique what their company is doing because they're not looking at just one solution. They've got three different solutions. They call them the pillars for sustainable, flexible packaging. The first one is really looking at monomaterials, polypropylene, polyolefin, creating layers of these, and then putting maybe different coatings in between that could be barrier coatings. So they create a barrier material where they maybe wouldn't have had it with just a simple structure. What's really unique about these structures is now that they are very compatible with mechanical recycling. So you're not worried about creating these structures that can't go in the recycling stream. So that's very exciting. Bio-based materials are still a key area where people are looking at natural resources for growing and developing things and changing them into polymers. That's always a big area. And one area that's really growing is paper, fiber-based, putting coatings on these things that also not just creating them, but also making sure that they're good with the recycling stream as well. And I think that's a great solution overall. Other things that we tend to see is the incorporation of these post-consumer recyclables in biofillers. So people are using more and more recycled content. Is a good structure to do. Also in areas where maybe things were overpackaged with these heavier polymers, companies are looking to lightweight the packaging as well. So there's a variety of things that are being done to move forward with sustainable packages. I think one thing I'm going to focus on is really the paper and the coated papers that are being developed. When you look at a paper, and this again is another slide from Bob's, I thought it was a really good one. And a picture on the upper right-hand side shows a conventional polymer. It could be polypropylene, polyethylene, PET, all that neat stuff. You can kind of think of your potato chip bag, where you open it up, you look at it, it's a metallized structure. That's very typical, where they add the metallization to create a barrier. And to do that, things have been optimized over the years, but what you have usually is a very smooth surface of that polymer, where you can then put your coating onto it. The polymer itself would be pinhole free or defect free, so it's a nice, good continuous film, and it's also non-hygroscopic, meaning that it doesn't swell. Let's say it goes into high humidity, it doesn't swell, doesn't fall apart. It's actually very, very stable. And that's pretty conventional, and that we've been using those day in, day out for many years. So one of the things that are being developed now is paper-based substrates. And paper-based substrates have a lot more challenges to them. the surface itself that you're trying to apply the coating to is rough. So you need to get your coatings to stick to it and be applied to it. And there's a lot of variability to it, a lot of variation. The substrate itself is porous in nature. I mean, we use paper as filters and the like. So when you have a very porous substrate, then you have to fill those pores with your coating, and really make sure that it fills very well, blocks everything through to get the barrier that you want. A challenge is that paper itself is very hygroscopic. It can swell in the presence of high humidity. You take it to an extreme, and it can totally just break down and fall apart in a very like jungle-like high temp, high humidity environment. As it can swell, it can also shrink. And so dealing well with the shrinkage and the expansion is a lot trickier to do with if you're trying to apply a coating to it and then also have it survive its life cycle as a package in its life. So there's a lot of nuances in art and challenges with coated papers, and creating them and the like, and making sure that they're good. On a similar note, there's also challenges to testing these materials. A typical permeation test is shown in the upper left-hand box. We have a process where there could be a test gas, could be oxygen, could be water vapor, could be CO2. Depends on what gas of interest we are that we're needed for our package and the shelf life of the product. And you see like a high cluster of gas over here on the left-hand side. And then what's going to happen is that gas wants to absorb into the surface of the packaging material, and then wiggle its way or diffuse through, and then come out on the other side. So if this was like a pouch wall, let's say, and let's say we have oxygen out here and maybe coffee on the inside, we want to make sure we've got a good barrier on that structure, because we don't want our coffee to oxidize. We want it to taste nice and fresh when we brew it. So this is kind of what happens in permeation tests. And the way we test the sample is we put this material into a diffusion cell. And that's what this blue line here is in this water vapor method, ASTM F1249. And on one side, we'll challenge it with a test gas. In this case, is water vapor, a controlled humidity. So to measure how much water permeates through it, we're going to sweep a dry nitrogen gas on the other side. And any water vapor that sweeps through it, transmits through it, is picked up by that nitrogen carrier gas, brought to a detector, and it's quantified. And this methodology, this method ASTM F1249, and there's other international standards as well that's based on this, has been around forever, and it works great for polymer samples. However, if you've got a paper sample and it's a coating on it, but let's say the coating isn't great, maybe there's open areas, so now there's porosity of the paper that allows water to actually be kind of pushed through here, or cracks in the coating and the like. You could get kind of erroneous results or very high transmission rate results with such a sample if it really isn't a nice, pristine, good coating on it. So what we look at sometimes, if we're given films like this, where we can have like flow issues or things like that, where waters actually can go through it very, very fast, and the coatings aren't very good, we'll use an older test, a more traditional test called an ASTM E96. This is a gravimetric test. And we take that coated paper and we attach it to what we call a cup. This would be a vessel that holds desiccant. We take that cup and we put it inside of a chamber with a controlled humidity. It could be 50% RH, could be 90% RH. It could be whatever we want it to be as long as we're controlling it. And 50% RH is actually very common for papers. And what happens over time is water permeates through the material. It collects within this desiccant, this calcium chloride desiccant. And what we'll see is the weight changes over time, and it actually starts getting heavier. And by plotting that weight change over time, I'll get a positive slope, and I use that to determine what my water vapor transmission rate is into the cup. So what we do in our laboratory here is if the materials come in and they're not as pristine, or there's some issues with them, like there's a coatings are cracked, or there's holes in the coating or things like that, we can still do a water vapor test to understand how things are transporting through them, but we'll use this alternate method for doing it. For oxygen transmission rate, the testing itself is also similar to what I showed for water vapor. The material itself, again, it would be this blue material here that's mounted in this diffusion cell. Oxygen will flow on one side, our nitrogen carrier gas flows on the other. Any oxygen that then permeates through that material gets picked up by the nitrogen carrier gas stream, brought to our detector and quantified. And just what I mentioned before with the water vapor, if there's any holes or cracks or anything with the paper, um, we can get erroneous results. You can actually like push oxygen through, overrange our sensor, and you just get a very low result. Sometimes what happens if the equipment isn't set up right, you might actually have a little bit higher float over here, and you push the nitrogen through this way, kind of diluting it, and you get an artificially low result. So any material that isn't really hermetic, that isn't a great barrier, uh, isn't really set well for a normal kind of this gas flowing instrumental test. So the common test is D3985. If you have a higher transmission rate samples, which coated papers are, F2622. This utilizes a different detector. It's still an oxygen-specific detector, but it's for higher levels of oxygen that you often see with coated papers. If the material isn't pristine and we've got those issues, we can still test it for transmission rate, but we use a different method. We use an accumulation method called ASTM F1306. What's interesting here, and here's the apparatus, is we've got a bottom cell here. It's a volume. We mount the film here on top of it, and then we kind of clamp it in place. We have this open then to room air up above it. Underneath the cell, in this volume in here, we'll purge it with nitrogen gas. The goal is to get the room air out of the cell and get it down to a very, very low oxygen concentration underneath the film. And then what we do is we turn off our flow of nitrogen gas that's purging through the cell, and we allow the oxygen to permeate through the film and collect down here in this volume under here. And then we graph that. It's similar to the graphing I talked about with the water vapor test, where we look at the weight gain over time, except now we're looking at percent oxygen over time. Here's a chart that's overlaying percent O2 that's accumulating underneath the film. And then if we know what that oxygen that's accumulating is, and we know what the volume is underneath our cell, we can actually convert that to cc's or milliliters of oxygen. We know what our film area is, our test area is, and we get transmission rate out of it. So our instrumental method here now is an accumulation method, but it's automatically then calculating what our transmission rate is. You can see for this sample, we're up near 10,000 cc's per meter squared day of oxygen permeating through that film. So that's a very, very high transmission rate sample. Some nuances and special challenges. Okay, I talked about how papers can be a challenge because of maybe the coating isn't fully intact and the porous nature of the sample, and you can have things flow through it. Porosity is a big deal. When we actually look at it, and I kind of zoom up on it, here's a sample that is mounted in a diffusion cell with the test gas flowing on one side, carrier gas flowing on the other. And what happens with this sample mounted in the diffusion cell is out here is our atmosphere. And in the atmosphere, we have oxygen. We have 20.9% oxygen. If we didn't have it, we'd be hurting because we need it to breathe. We also have ambient humidity out here as well. So what can happen, especially when you've got something that's porous, I think of this as like a sponge, really. In that, yeah, I have my oxygen test gas here, but I got ambient oxygen that can permeate in through the edges and add to my measured transmission rate. And that's not the goal of the test. The goal of the test is trying to understand what's going perpendicularly through my film. So to kind of solve that, that problem is in industry, one way to do is orientate it with a barrier to the carrier. So let's say I put a metallization or a coating on my paper substrate. Well, if my paper is oriented this way, so my barrier is now facing my nitrogen carrier gas, and my oxygen's facing here, even if I do have some oxygen kind of leaking in from room air coming in through the edges, it's not adding to this so much because I've got this barrier layer here. It's just not going through. So this is a very traditional way of testing a barrier sample, say, or a coated paper sample, by having the barrier to the carrier. So that's utilized a lot. Another way that we've done, a lot of our customers have utilized, we've done in our laboratories, we mask the sample to kind of a smaller area. So it doesn't come all the way out to the edge of our diffusion cell. It'll be a smaller area inside. And then because it's a smaller area, we also then go mount this in a way that where we encapsulate the edges. So we can't have any gas, oxygen, water vapor kind of permeating through there. So that works out really well. It is a kind of an art project in a lot of ways, a little more setup involved in order to prep it this way, but it works well. It definitely can work well. To kind of to minimize that kind of extra prep, our company Mocon has really developed a couple different what we call cartridges. These are systems that we can then mount a sample into without using the epoxies and without using extra kind of art in the prep. One of them is this edge effect cell, and it's designed in a way that the edges that would be exposed to ambient are closed off, and we've got some O-rings in here, and we actually flush it with nitrogen here. So we can't get room air flowing in through the edges. It gets sealed off, and that can work very nice. There are some samples that may be just so thick that they don't really work well for this compression, or it could be like a cardboard or some maybe fiberboard in some way. And maybe they've embedded a thinner layer in the middle of it. We see that with complex structures. For those types of things, we have something called a compression cartridge, where basically we clamp down on it. We have these little rigid areas. I'm going to say kind of like knife edge, but it's not really like sharp like a knife, but it pinches. It pinches us very, very tight. That way it minimizes or eliminates anything that could maybe come in through the edges. And that's a solution that works for a certain niche or variety of samples. But for the samples it works for, it works really well. So for what's going on with these paper challenges, I talked about what can be moving through it with cracks and coatings and porosities, but the edges of the sample are very important to understand as well. So I've got this film, and talked about testing it. One of the another ways it's important to test it is the finished package, the pouch that we're going to make out of it, or the tray with the lidding, or however we're using this material. And for pouch testing, the typical pouch test that's really outlined in ASTM F1307, it's oxygen transmission rate pouches, is to make a slight, incision in the pouch, insert these tubing lines that allow nitrogen to flow in, sweep inside the pouch, and then flow back out, back to the instrument. And, it talks about hot melt or epoxy. We use epoxy. Hot melt itself also is permeable to some degree. And then the pouch would be then exposed to room air outside of it, 20.9%. And what's nice about this type of test is we're measuring what's going in through the face of the film, but we're also now measuring what's permeating through the heat seal of the edges of the pouch as well. And then also if you have a pouch that has, let's say, a zip seal type seal, what can be permeating in through that as well. Here's a close-up of a pouch. This one would be like a medical or pharmaceutical pouch where it's foil. It's a good barrier. And here would be our slight incision. Here's our tubing lines, and we've epoxied it in place. What I want to discuss with this is, boy, if this was a coated paper, a lot of times the coatings are on the sealant layer, so they'd be inside the pouch. That's what would be touching the product. That would be the barrier area. It's important that if you're testing a material like that you put the epoxy not just only on the outside here, but get some on the inside. So on the inside of this, it's also sealing kind of all the way around on the inside of just this little area. So we've got a good seal there. If we didn't do that, and if this was just paper, only paper on the outside, what could happen is, due to the porous nature of paper and the tenacity of our oxygen, water vapor, and the molecules, they could actually permeate through the paper, but under the epoxy and kind of like do an end around and come into the package. So if this was a coated paper pouch, we'd want to make sure that, again, we've got good epoxy all the way on the inside of this and on the outside. So it works out really well. If this is kind of too artsy for some people and are hard to do, or just shows a little bit more variation when you're mounting multiple pouches like this, we do have a tool that we came up with Mocon here, of where we have a piece that we cut a little bit of a bigger hole in the pouch. We've got a piece that slides inside of it, and then this that clamps on the outside of it. kind of screw these together, and we're mechanically clamping on the inside and outside of this. I don't know if this photo does it total justice, but it's got a mechanical seal. And I've got an O-ring here, so I'm sealing well to that inner layer, the inner sealant layer. So I've got a really good bond and a really good seal. So this is what we call a pouch cartridge that we have that allows us to test pouches with more of a mechanical seal versus using that epoxy or hot melt type method. So that's kind of really important if you are looking at papers, coated papers, and looking at not just the papers and how to analyze them, but also as you start forming them into packages. Analyzing them and knowing the right way to analyze those is key. Um, I guess the way I want to end this is our laboratory here is the world leading permeation laboratory where we support hundreds of companies with their sustainable packaging initiatives. And things to take home are that there's not just one test, one defining OTR test or one defining WVTR test that works for all samples. And even if you have the right method, it still may need to be a little bit more detailed on how that package, how that sample is mounted, what nuances are needed. And with our laboratory here, with our experience of testing thousands of packages, we have that experience behind us. And not only that, we have the tools. So if one method doesn't innately work, it has a lot of variability, we can go, we talk with our clients, we figure out what is the best method to utilize. And that's what we do. So I want to thank you for listening to this presentation. And if you do have any questions, you can feel free to reach out to me, Joel Fischer, at AMETEK MOCON. And I wish you a great afternoon. Thank you.